Right. All right. So today, remember we got to cut early, so we're going to finish up lists and list-based data structures. We already really finished up lists already with array-based list and linked list. But just as an end cap to that, I do want to mention several variations on linked lists, including doubly linked lists, which would include basically you have each node not only keeps track of the next node, but also the previous node. So that if you want, you can travel in both directions. You can go next, 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 or you can go previous, 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 previous. So you can go back and forth on those. And it just doubles the complexity a little bit in that each node now has to keep track of both directions. The tail, the next would be null. The head, now the previous would be null. And everything else would have both references defined. Now, inserting something, of course, means that you are going to have to change 2 references and then change 2 more references, so 4 references total. You can have circularly linked lists where there is no head and there is no tail. Instead, the head or the tail just points back to the head, and so you've got this one big giant circle. And that facilitates, algorithms or data structures where you need to go around robin to different things, like a token ring network. Nobody uses those anymore since we've got LANs and routers and stuff. But it used to be that you could network a bunch of computers together by just making them into a circle. And then the way that they talk to each other is that everybody got a slice of that network at a particular time. First, it was the first computer's turn, then the second computer, then the third, then the fourth, then the fifth. And that's also how interrupt requests work in operating systems and stuff like that. Yeah.
Is that what cars use when they
The cars?
cars, yeah, for communication systems?
It could be. You have to come up with some protocol where everybody gets a turn to talk, or some asynchronous where everybody can talk at once, and it's multiplexed or something like that, where everybody can share the channel at one time or at the same time, or cut it up into discrete times. There are various network protocols that do something like that. You also have unrolled linked lists, which are basically a hybrid of linked lists and array-based lists, in that each node is not just one element, it's an array of elements. And so then you can link one array to the next array, to the next array, to the next array. So one array could be like 100 elements, and then the next array is linked to the next array. It's just a reference to the next node that contains 100 elements in its array, etc. And it's kind of a mix between the two, because if you think about it, where you only have one node and an array inside that node, that's an array-based list, right? If you think about the other extreme, where it's an array of size 1, well, that's a linked list. And so you can tune that back and forth to get basically a hybrid of the two algorithms if you want performance trade-offs between the two. And finally, skip lists are basically linked lists, but that contain additional references. So, for example, you can have like 100 elements. The head points, of course, to the next, but also it points to the middle element, so that you can skip 50 of those elements if you need to get to the second half of the list. Right? Again, another extreme would be if you have total random access, then everything is essentially linked by doing pointer arithmetic. And this allows you to skip, to give you something that looks kind of like a binary search, in that you can jump to the middle of the list and determine, I need to go to that half or that half. And so you can jump back, or you can jump forward again, or something like that. And then you can cut it even smaller, so that it not only contains a reference to the halfway distance, but also to a quarter distance. So you can jump to a quarter, or back and forth, back and forth. And the more pointers you have, of course, more references that you have, the more you're getting towards just an array-based list. So it's also a trade-off there. How much are you going to splice that list up? But you also pay a price, because eventually, it's going to get completely referenced. So everybody will have a reference to everybody else, and it's no better than an array-based list. And so you'll need to reconfigure what that list looks like. Those are all variations of linked lists, array-based lists, etc. Okay. What we're going to look at now is a variation, but with respect to behavior. All right. So we're going to be looking at now let me go ahead and go with this, stacks and queues. Queues, there we go. Got to spell it correctly. So collections, that is like the ones that we've looked at so far, lists and sets, are unstructured. Remember that we're in the point in this course where we're looking at data structures and algorithms. Why do we use that word structures? Because we like structure. If something has structure, that structure can be exploited. If it's completely unstructured, it's just stuff sitting there, like in a set, you may not necessarily be able to exploit it that much. But as you add more and more requirements, more and more structure to the data, then you can exploit that, right? Lists in some sense are a little bit structured. Lists have an ordering, right? There's a first, second, last element, etc. Right? But, lists are not necessarily sorted. I could have a list of 5, 4, 10, right? And there's a first element, a middle element, and a last element. But that 5, 4, 10 is certainly not in any order, right? It's not in ascending order. It's not in descending order. Sorting imposes a structure on a list's state. This goes back to object-oriented programming, right? What is an object? An object is has state. It has behavior, methods that act on that data, and identity. What we're talking about here is ordering imposed on the state. What we're going to be looking at is are what are called restricted access data structures. Right? These impose ordering on the collection's behavior. In other words, we're not just going to allow you arbitrary access to this thing. You insert it at any index, retrieve from any index, et cetera, et cetera, et cetera. Instead, we're going to limit your approach to it. And by limiting your approach to it, we're basically adding structure and order to their behavior, potentially giving us some really, really efficient operations for certain applications. Okay? So again, we really like structure. Why? Structure can be exploited for efficient data processing and algorithms. So let's take a look at stacks. Go ahead.
Exploited sounds like a negative thing, like something you don't want to have happen. Would you consider that to be a negative?
I would not consider that to be negative in this context. You exploit low prices, right? You exploit a discount. If as long as it's within the rules, right, you're exploiting it, right? Utilize if you prefer, but the same idea. Right? So a stack is a data structure that stores elements in a LIFO, that is last in, first out order, manner. Oh, I'll say manner, okay? You've seen stacks before. Where? In what context? Or you've heard the term stack before. Stack Overflow. Why? In what context is that? The program stack. Function A calls function B, calls function C, calls function D. How do you keep track of which function called which so that you can return to the calling function? You have a program stack, right? And the program is loaded up. There's data in the program, whatever. But now the main is loaded. The main calls function A, calls function B, calls function C, calls function D. Those are stack frames that are placed on top of the stack. When you return to the calling function, those stack frames are popped off the top of the stack. And now what's on the top of the stack? That's your current context, right? Very, very efficient because you can keep track of all those breadcrumbs like Hansel and Gretel coming out of going into the forest. You leave the breadcrumbs behind you, and as long as they're not eaten, all you have to do is follow the breadcrumbs back to find where you came from, right? And it's because of the last in, first out manner that we have that restricting of behavior gives us that structure. It's like a stack of dishes where you can't necessarily pull a dish out from the center or the bottom, right? You're only allowed to pull a dish off the top. And how do you put the stack of dishes? You don't shove them in the middle of the pile because it'll fall over. You only put it at the top. Right? We've got a linked list representation of a stack here. You'll note that it's vertical now. Up here, the head is being treated as the top. The tail is being treated as the bottom. So there are two basic operations that we can do with this stack. We can put stuff in, take stuff out, but only from the top. So if I pop something off the top, right, I pop it off the head. Right? If I push something onto the stack, like 58, then it also goes onto the head. Right? So that the last one that I put in, 53 in this case, is the next one that I pop off the top. Right? So, a couple questions here. What happens if I pop too much? Pop one more, and now it's, how would you characterize that stack? Empty, right? So if I pop one more time, what should happen? What could happen? What will happen? An error? Okay, we could throw, like in the context of Java, we could throw an exception. You can't do that. You asked for something that doesn't exist. I'll throw it back to you as an exception, let you handle it. What's another option? Do nothing. In which case, I would return back to you nothing. And in the context of Java, nothing is what? No, right? Or we could just be silent. Right? Nothing. Now here, if empty, do nothing. I like their terminology here. Right? Now, in general, stacks are unbounded, but we know that that's not true in practice, right? I asked what the context have you seen stacks, and you said Stack Overflow. Right? When you call a function calls function too many times, you fill up your stack, and what happens when you try to call one more function? Stack Overflow. That's a bounded stack. You're only allowed to put so much on that stack. If it's unbounded, there's no problem. You put as much stuff in that as you want, right? But you can have bounded stacks where I'm only going to allow 100 things to go into this stack. In which case, what happens when we've got 100 things in there and then you add one more? Well, Stack Overflow, but what should we do in the context of Java? Do nothing? Throw an exception? Quit out of the program entirely, right? So those are all design questions that we need to come up with as we implement this stack. All right, I'm going to go ahead and create a new class, and I'll call it a stack. And I'm going to parameterize it from the beginning because I already learned my lesson from an array-based list, right? So we're going to have those two public void push, an element item, right? And public void pop. Oh, sorry, not void, but if we're going to pop it off the top, then I'm going to give it back to you. And so our return type here is going to be an element of type T. Okay? Those are the two basic operations. Put stuff on the top, push, and take stuff off the top, pop. Okay? Now, I need to ask another design question here. How should we implement this stack? Okay, let's use a linked list, right? And what do you mean by that? Should we extend, what was it, my linked list? There. Is a stack a linked list? Is a linked list a stack? So we're backwards here. Or neither? Or both? Can you have an inheritance hierarchy that's self-referential? Oh, that's a time paradox, right? You're your own father, right? Oh, it's happened in Futurama, right? Or you're your own great-great-grandfather or something if you travel back in time, right? So, no, we don't like that, do we? That seems weird. So we don't like that in our inheritance hierarchies either, right? So it can't be both, certainly. Is a stack a linked list, though? If I did it like this, yeah. What would be a problem there, though? If I did it like this and it compiled, well, here, let's return null so that it compiles. Let me go over to my demo here and create a stack. What can I do with it since it's a linked list? S dot, oops, not integer. There we go. S dot add to, or let's get element at index 5. Does that sound like a stack to you? Something that you can arbitrarily take out any of the plates? No. Insert element at index 5. Does that sound like a stack to you? No. So I don't like that inheritance there. Oops, sorry, let's go back to stack here. What about the other way? So a stack is not a linked list. Is a linked list necessarily a stack? That doesn't sound right either. That sounds even less right. So instead of locking this into an inheritance hierarchy, let's go back to our thinking on object-oriented programming. And one thing I mentioned there when we did OOP was, in the context of inheritance, prefer composition over inheritance so that you don't lock yourself into a hierarchy. What does composition look like in this case? Not public, private, my linked list, underlying list, right, equals new my linked list constructor. Space, there you go. That's composition. Now, inside of our stack, we've got a list where all the operations are actually occurring. But from the outside, it looks like we only have a stack. Push, pop, that's it. Right? Because we've closed off access to the outside world by changing the inheritance, or not the interface entirely. Right? We're not locking ourselves into that hierarchy of one thing is another and inherits everything from above. Right? What does push look like then? Well, what did push look like over here? Let's create a new random push. 94. Add to the start or add to the head, right? So dot add to start. Right? X, or item. There we go. What does pop look like? Oh, remove pop. Remove element from start or head, right? By the way, head, tail, it doesn't matter. Flip this upside down. Turn your computer upside down. It doesn't matter, right? It's just an orientation that the dish metaphor makes sense to us because of gravity. Right? All right, so underlying list dot remove, and we never did that. Remove from start. There we go. We never did that, so let's do that really quick. What does that look like? Add to end. Oh, where's add to start? I want it right next to it. All right. Public t remove from start. Well, what did it do over here? It took that thing out of the node so that it could eventually return 73. So let's store that off into a temporary variable here. This dot head dot get element, right? And that's what we're eventually going to return. And now we need to destroy the head. Did we have remove head or something? Remove from start? Nope. So what does that look like? Make the second one the new head. This dot head is equal to the current head next. Now, if there was only one element there, then what would happen? The next one is already pointing to null, so now the head is null. Empty list, exactly what we would expect. What would happen if the list was already empty, though? Probably a null pointer exception. Why? Head would be null, so you can't get the element stored in it, so it would throw a null pointer exception. Would you expect that over here, where all you have is a stack, and it says the head node is null? We'd be like, what the hell are you talking about? I have no linked list here. I have a stack, right? So let's go ahead and continue. We'll deal with that in the stat class here in a moment. Yeah, go ahead. It'd only be null if the list was empty. No, I mean, you wouldn't be able to get the element because the node doesn't even exist. Right? So we'll come back to this. What else do you need to do if you're taking something out of your linked list? If there were 5 elements before, how many are there now? There. Okay. Let's go over here to our demo and let's push a bunch of things. S.push 10, 20, 30. And then let's pop them all and print them out. What order should I get? Which should be at the, if I goes 10, 20, 30, LIFO says 30, 20, 10. 30, 20, 10. Right. Yeah, you can see that online. Okay. What if I pop one more time? I get that null pointer exception. Does that sound right? Null pointer exception, my linked list. I never made any linked list. Leaky abstraction there, right? It's leaking information about how you've implemented your stack. And so let's not have that. What happens, what should happen when you pop from an empty list, or from an empty stack? If this dot underlying list dot is empty, we should handle that here. You asked for something that doesn't exist. Return null. That's one way. Return nothing, do nothing. What's another way? Throw a new illegal state exception, whatever exception you want to come up with. You cannot pop on empty stack. That's good enough. All right. So, which one do you want? I'll go. Yeah, there you go. But really emphasize. Which one? Which one would you want if you had to use this stack? Throw an error? Okay. What would happen if I return null? There's no information, in fact, there's ambiguous information. What if I push 10, 20, 30, and then I push null? How would I know that when I get null back, that that's something that I pushed previously versus there was nothing in there, so it gave me null, right? There would be, I would have to design this a little bit more with additional functionality for you to be able to disambiguate those two situations, right? Something else that you could do is a capacity to do. Consider implementing a maximum capacity, right? What would that look like? Max capacity is equal to 100. I'd probably take that in part of the constructor, right? And so if you tried to push onto a full stack, if this dot underlying list dot size is equal to this dot max capacity, then what? Yeah, we don't want more than 100 elements. Throw an exception or do nothing, right? Nope, equals. Or we call this noop, or no op, no operation, do nothing, right? That's only if you really want this max capacity. Another side functionality, another secondary functionality is this operation called peek. So what are you doing when you peek? You're taking a look, but you're not touching it, right? That means that you are retrieving, but not removing the element at the top of the stack. 86 in this case, right? All right. So actually, let's save this and let's run it again, showing you that you cannot pop an empty stack, right? Now there's no leaky abstraction at all. That is all in terms of the stack instead of the underlying implementation. So let me go ahead and get rid of that causes that. And let's go ahead and implement the peek method over here in the stack. Public t peek. What would that look like? get element at index 0. Right? Cool. Right? A stack implementation with reusing. So the whole point of inheritance is that you inherit behavior, that you reuse that code. Composition provides another way of doing code reuse without locking yourself into a hierarchy if it doesn't make sense. Right? Yeah.
Would making the underlying list private make it so that you can't call, like,
It protects it. That's good encapsulation. Right.
the underlying lists, like, for like the my linked lists methods as well?
Exactly. I can't access that, right? Because it's private. That's encapsulation. I'm protecting my data. I'm protecting the internal workings of my class. Right? Only I, now I'm the stat class, only I may screw around with that list over there, right? You can call push, you can call pop, you can call peek, but you can't call anything else with respect to the underlying list. What if I change this? Remember that my list is that array-based list. Now I'm wishing that I'd call it my array list. What broke? Well, that broke because we didn't do it. That broke because we didn't do it. But if we did them, then of course it would work, right? But an array. I've got an array. If I'm working at this end, I need to push something at this end. What am I doing with all the elements? Shifting them to make room for it. When I take this element out, pop, I have to shift everything down, right? So what end should I work from if I do this with an array-based list? Not this end. If I do it from this end, no shifting at all. Put stuff in, put stuff in, put stuff in, put stuff in as much as you want. Take stuff out, take stuff out, take stuff out. All this stuff down here doesn't get shifted at all. Picture it like this, vertically. The stuff down here never gets moved. Well, it's only the stuff at the top. So you can do this with an array-based list, but you just have to be careful to work from the correct end. Yeah.
So you would essentially put the last stuff first and the first stuff last.
Yeah, your head, you would work from the tail instead of the head. This works from the head. By the way, if we worked from the tail, we'd have the same problem because we never implemented the tail on it. Right? We only implemented the head. If we implemented both, you could work from either end, whichever end you want. Right? Okay. That is stacks. And again, I'm going to go ahead and cut and paste this. So the last element to be put in the stack is the first one to be removed. It has two basic operations, push and pop. You can call, or you can work from either end if you've supported both ends. You can do an array-based list. You just have to be careful to work from one end or the other. And of course, you have many applications. Call stacks, we've already mentioned. Keeping track of breadcrumbs in general. If you're walking through a solution space, or if you're walking through a graph, DFS is something that we'll look at, but in the context of trees, then you can very easily use a stack. You can use a stack to simulate recursion so that you're not actually calling function after function after function. You're just pushing data onto your in-memory stack. And then you don't risk stack overflow. There's also the shunting yard algorithm. Anybody know what a shunting yard is? No UP family, Union Pacific. All right. Shunting yard is from trains, where the train backs into the shunting yard, disconnects somewhere in the middle, and then pulls out again. Right? What are they doing? They're backing into the shunting yard so that it can be disconnected and go its own way, and so that another train can come in, connect, and then take it out. Right? And so there's a shunting yard algorithm that does that for mathematical expression evaluation and stuff like that. You'll use a stack in your lab in a couple of weeks to do postfix notation. So postfix notation is a different way of adding stuff. So 2 plus 4, right? That's 6. Another way of writing that is 2, 4 plus. We put the operator at the end. Why? If you see a number, an operand, you push it. Push 4, push 2. If you see an operator, you pop, and operate on them, and then you push the result back into your stack. So that that's called postfix notation. Instead of, the advantage there is it does not require any parentheses at all. There is no order of operations issues. And if you get really good at it, then you can use an HP calculator. Have you seen HP calculators? Or some like an accountant, an old school accountant using an HP calculator, maybe type. They're blazingly fast because they don't have to sit there and write down an intermediate result and then deal with an order of operations issue. Right? They could just sit there and type, enter, type, enter, and the result gets pushed, and the memory keeps track of, however many results you have, and then operand, pop. Right? You can get if you get good at it, you can get blazingly fast and much better at adding stuff up. Yeah.
I'm sorry for the ignorance question. Operand versus operator.
2 and 4 are operands. Plus is the operator.
Okay.
Right. Likewise, plus, minus, subtraction, or multiplication, division, those are all operators, and the numbers or variables are operands. Right. Okay. Additional functionality would include get the size, peak, etc., retrieves, but does not remove the top element, and many other additional pieces of functionality if you want to get into it. The sister of stacks are queues. So if a stack is a stack of dishes, what is a queue? British speak. British call these things. We call them, instead of queues, we call them, oh no, nobody watches Doctor Who or anything. What? A queue, you queue up, that's just a line, right? It's a line. Right? Queues are essentially lines. Right? They're FIFO data structures. First in, first out. Right? The first one to get into the line is the first one to be served. The last one to get into the line is the last one served. Right? So you can think of it as people get in. How do you queue up? How do you line up? You get at the end of the line, and then when you move forward, and who's gets served next? Whoever's at the head of the line. Head of the line, end of the line, or tail of the line. Right? And we've got yet another way of representing this, again with a linked list. Right? Here's the head of the line, here's the tail of the line. The operations here are NQ, get in the line, and DQ, get out of the line. So if I NQ something, it gets put in at the end of the line. Right? If I DQ something, whoever's next is served next. Right? And at least on this simple example, we don't allow line jumpers. We don't assume that anybody gets tired and I don't want to wait here anymore and leaves, right? But that you can do that, right? Expiration queues or priority queues, something like that. So there's no cuts, right? It's a first in, first out data structure. And once again, we call these NQ or DQ. Now, I like this simulation here because it uses those proper words. Some implementations will use the exact same terminology of push and pop for a queue. I think that that's terrible practice because it uses the same words for fundamentally different operations. Otherwise, offer is sometimes a synonym for this. And I think that it comes from the idea that when you get into a line, a very long line, you don't just stand there. Right? I mean, most lines you do stand there, and so you're forced to stand. But other more organized places, you take a number, right? They offer you a number, right? And then when they want to help the next person, they call out, "We're now helping number 24." Then after that, now we're helping number 25, right? Now we're helping number 26. And that's pulling. Who's next? Did 25 leave? Okay, well now we're handling number 26, right? And so offer you a ticket, offer you a number, pulling who's next. In either case, you're working at two different ends of your list. It doesn't matter if you go in this way and go out that way or the other way, as long as you're consistent about it. What would that look like as far as Java code goes? New, class, queue. Public, void, enqueue, t item. And public, t dequeue. Come on, can't type today. All right. Well, first again, what do we have to do? We have to decide, are we going to put it into an inheritance hierarchy? Probably not, because a queue is no more a stack than a stack is a queue, and neither one of those is a linked list or vice versa. Right? So same solution. Let's use the linked list. Instead of using that linked list, though, I'm going to use Java's linked list. Private linked list underlying list equals new linked list. I have to import it. There we go. And now, enqueue operation is what? Add adds to the end. Add first, add last. Neat. Add first. A dequeue operation would be remove, or remove all, or remove first, or remove last. Which one would we want? If we're adding first, then we would want to remove last. You could go the other way if you really wanted to. You could go remove first and add last if you wanted to. It doesn't matter. Turn your computer upside down and it's the other one, right? Oh, and then we have to return this.
Is it because semantically, like, it's defined by the add first versus remove last?
Yeah, there's a head and there's a tail, and I think that this is a doubly linked list, so we can check it out. It's a class. Ooh, they've got a node class. Funny coincidence. Right. And what do they have there? They have an item, they have a next and a previous, so it's a doubly linked list. Right. And the linked list itself, the linked list class, takes care of the first and the last, or the head and the tail. Right. Don't roll your own. Use a linked list. Don't roll your own queue. Use what's called a deck. And for that, I'm going to wait until next time, but Java deck. D-E-Q-U-E. It's pronounced deck, and it's called I don't know why it's called that thing. I'm not even sure if you looked up in a dictionary that you could find it. Maybe just a computer science thing. But a deck is a doubly ended queue, right? You can work from either end. It's just an interface. Right? So you have an array-based deck, which is an array-based list. You have a linked list, which is a linked list-based deck. What behavior do you want? Do you want to work at the head, or do you want to work at the tail? If you want to insert or remove or examine, in other words, peek, what behavior do you want when when you pop something off of an empty queue? Do you want it to throw an exception, or do you want it to return a special value? Null. That all determines which of these methods you want to call. So this one implementation, this one interface and its two main implementations give you everything that we just talked about over the last week. Right. So don't roll your own. Use this guy. Yeah.
What would be the purpose of making our own list? Like what?
For the class? Because you got to do it, because I said so. As an exercise, right? So you know how these things work. In practice, you don't reinvent the wheel. Right? You are reinventing the wheel for this course, just like if you took an automotive class, you would disassemble and reassemble a car, even though, unless you're going to be a mechanic or something, you don't do that. You go to the dealership and you buy it.
That makes sense.
Or if it's, I guess, two shifters, do you work on cars too then?
I buy it from
Oh, okay. and then fix them up. Okay, so mechanic right there, right? So you do reinvent the wheel.
Reinventing the wheel gives you a better idea of how the wheel works.
Exactly.
Easier.
Exactly. All right, so we'll continue next week.